Welcome to Study Loop.
Okay, so we're doing chapter 29, problem 11. So this says, in a region of space, the magnetic field points in the positive x direction. So we'll call this positive x B field, and the magnitude is given as an initial magnitude B naught plus B times x, with B naught and B greater than 0 when x is greater than 0. So let's call this our xy plane. So our origin's over here. Cool. So it also says a flat coil, so n equals 1, with an area, moves with uniform speed v from right to left with a plane always perpendicular to the field. So let's draw this here, and v is moving this way towards the origin. Okay, cool. So now it says part A, what is the induced EMF of this guy? So Faraday's law, of course, says the induced EMF is given as a negative change in magnetic flux as a function of time, or rate of time. So now we got to figure out what is the flux to figure this out. So the flux is given as the magnitude of B times the cross-sectional area. Okay. But B is a function of x, right? So this flux changes as a function of x. So this is B naught plus B times x times the area. So now when we take the derivative, d phi b dt is a B naught. That has no x dependence, so that's just gone. Okay, so then we have a times little b times dx dt. But dx dt is just the velocity that this is changing, right? So this is a b times v, but v is in the negative direction. So this. So that means EMF is negative the derivative of the flux. So that means this is just a times v times v. Perfect. So part B. So now it says as viewed from the origin. So here's the origin, right? So we're here looking this way. Imagine that's kind of hard to picture yourself over there. We got to figure out what orientation is the induced current. So the flux is decreasing, right? We already found out that the rate of change of flux is negative. That means it's decreasing. So to oppose that, the induced current must point in the direction of the B field to the right. So if we're looking at the origin, imagine that using the right-hand rule, we need the induced current to be like this, or induced B field. So to do that, it's got to be a clockwise current. It's kind of tricky to imagine yourself from over here in the origin looking that way, but that's going to be a clockwise just using the right-hand rule. Okay, so part C says if instead the coil moved from left to right, that means V is now the opposite, right? So that means, what would the answers be, right? So the induced current, right, the induced EMF magnitude is going to be the same because it doesn't really depend on the speed, the magnitude of it. So, but the directions, right, because of that, the flux depends on this. So the flux, the change in flux depends on that. It's going to flip, right? It was less than 0. Now it's going to be greater than 0. And because of that, we need the induced magnetic field to go the opposite way. So that's going to give you means you're going to have to use a counterclockwise induced current to oppose that. So it's an induced current if it's moving from left to right is going to be pointing counterclockwise so that the B field can point left instead of right